All right, hello everyone. Welcome to my channel. This channel is for educational purposes, and we like to look at great theories of everything, ancient and modern, and go deeply into them, help you to understand how to use them so that you can awaken to 5D consciousness, form your holistic worldview, and change your paradigms. So today is our 513th video that we've done on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson was an American engineer who lived in the 20th century, died back in 1990, but not before he put out many books, articles, and got a little bit of small following going. Some people who also wrote very interesting things that we've covered on this channel. And in 1959, Mr. Larson proposed his two fundamental postulates about how he believed the universe operated. And from there, he derived a theoretical universe, what his universe would look like if his postulates were correct. And then he compared his theoretical universe with the measured empirical universe of the modern scientists. And the results of that, some of those results are written up here in this book that we're looking at today, called Basic Properties of Matter, primarily on chemistry. We're in the middle of chapter 22 of this book called Magnetic Materials. If you like a rundown on the reciprocal system, how it works, what the fundamental postulates are, how it operates, what the ramifications of those postulates are, then you want to watch one of my first 474 videos on this topic. For the purposes of this video, I'm going to assume that you have some type of knowledge of the reciprocal system. If you don't, go back and watch one of those videos. If you don't want to do that, hang on tight. You still might get something out of this, because Larson sometimes explains himself along the way. But we're just trying to get through the material, and so I don't want to spend a lot of time, repeating, the basics, just to get everybody up to speed. Okay, so we're here in the middle of chapter 22. He's talking about the refraction constant, I believe, and we'll start right here. The average difference in initial level for a molecule of rotational mass m is then m prime over n over 9m. In table 34, this value, shown as delta I over m, change in current, is applied to the refractive constants of representative groups of simple organic compounds to arrive at the internal magnetic susceptibilities. The corresponding values from observation are listed in the last three columns of the table. Values marked with asterisks are taken from a recent compilation. Where no measurement was available from this source, a representative value from the earlier reports is shown in the same column. The last two columns show the range of results reported from the earlier measurements. Okay, so he shows these this table, and he's got several different columns here. and the last two are calculated and observed. And so we're looking at the paraffins, and it looks like he's not right on target, but within a few thousandths here with the paraffins. He's pretty much exactly right with nonane and butane. And then we move down, and it looks like the values are consistently very close, but not exact, to the compiled values for the paraffins. Now that doesn't necessarily mean that Larson is off. It could be that the values determined in the laboratory are off, as opposed to Larson's values, which he's determining in his mind, in theory. Then we go to the acids, and Larson is pretty accurate on those as well. Go to the alcohols. There's a few values here that look like they're a little bit low. So there might be a glitch in some of Larson's equations here. Looks like his values are consistently low for the alcohols, usually by about 2/300ths. Monobasic esters, again, a little bit low. Well, he's right on target here with propyl. And moving through all that, now we're headed to the dibasic esters. Pretty consistent values here. Well, a little bit off, but within 100th there. Amines, amines, off by a little here with diethyl, but cyclanes, benzenes, and yeah, so hopefully he'll sum it up here. In the normal paraffins, the association between the CH2 group and the lone hydrogen atom at the negative end of the molecule is close enough to enable the CH2H combination to act as the end group. This means that there are 18 rotational mass units in the end group of each chain. The value of delta I, change of current, for these compounds is therefore 18/9 equals 2. Branching adds more ends to the molecule and consequently increases delta I. The 2-methyl paraffins add one CH2 end group, raising delta I to 3. The 2,3-dimethyl compounds add one more, bringing this quantity up to 4, and so on. Very close association, similar to that in the CH2H combination, modifies this general pattern. In 2-methylpropane, for instance, the CH-CH3 combination acts as an interior group, and the value of the change in current for this compound is the same as that of the corresponding normal paraffin, butane. The CH3, the quantity 2 combination, likewise acts as an interior group in 2,2-methylpropane. and as a unit in with only one N group in the higher 2,2-dimethylparaffins. Each of the interior CH2 groups with the higher initial level adds 9 rotational mass units rather than the 8 corresponding to the group formula. This seems to indicate that in these instances, a CH2-CH2 combination is acting geometrically as if it were CH3-CH. In the ring compounds, the CH2 and CH groups take the normal 8 and 7 unit values respectively. The behavior of the substituted chain compounds is similar to that of the paraffins, but there is a greater range of variability because of the presence of components other than carbon and hydrogen. The alcohols, a typical family of this kind, have a CH3 group at one end of the molecule and a CH2OH group at the other. The value of delta T for the longer chains is therefore 26/9. In the lower alcohols, however, the CH2 portion of the CH2OH group reverts to the status of an interior group and delta I drops to 2. The methyl alcohol molecule goes a step farther and acts as if it has only one end. A similar pattern can be seen in other organic families such as the esters. Since we have found that the effective units of some of these compounds in certain of the phenomena previously examined are double formula molecules, it appears likely that the magnetic behavior of methyl alcohol and other compounds with similar characteristics can be attributed to the size of the effective molecule. No similar studies of paramagnetic materials have yet been made. Unlike diamagnetism, paramagnetism is temperature dependent. For an explanation of this dependence, we need to recall that magnetism is a motion. One of the significant advantages of recognizing its status as a motion is that its effect on other motions can be evaluated in terms of a direct addition or subtraction, rather than having to be approached circuitously by means of some hypothetical mechanism. Diamagnetism, which is motion in time, or negative, has no connection with the thermal motion, which is motion in space, positive. But paramagnetism is positive and has an imputed direction opposite to that of the thermal motion. Thus, an increase in temperature reduces the paramagnetic effect. The internal magnetism, which has been the principal subject of the discussion thus far in the present chapter, is of interest primarily because of the light it sheds on the nature and properties of magnetism in general. From a practical standpoint, magnetism is synonymous with ferromagnetism, F-E-R-R. No systematic study of ferromagnetism in the context of the theory of the universe of motion has yet been undertaken. There are, however, a few points about the place of this phenomenon in the general physical picture that should be noted. Ferromagnetism exists only below a temperature, the Curie point, which is specific for each substance. Inasmuch as this type of magnetism is restricted to positive elements and some of their compounds, ferromagnetic materials are also paramagnetic and exhibit their paramagnetic properties above the Curie temperature. In this range, the susceptibility is linearly related to the temperature, but the relation is inverse. That is, the relation is between temperature and 1 over psi, which I believe is that Greek letter, and I don't remember what it means. It could be the susceptibility. In one respect, there is a significant difference between the magnetic susceptibility and most of the physical properties discussed in the earlier pages. The specific heat of any given substance, for instance, decreases with decreasing temperature and reaches zero at a particular temperature level. There is no specific heat. There is no negative specific heat. Consequently, the specific heat of the individual atom is zero at all temperatures below this level. But magnetic forces act upon magnetic substances at all temperatures below the critical temperature as well as above it. What we have here is a difference in the significance of the 0 point. As explained in Volume 1, the true datum of physical activity, the natural zero, is unit speed, the speed of light. Natural physical magnitudes extend from this natural zero to the natural unit of speed in space, our zero, in one direction, and to unit speed in time, inverse speed, in the other. These two speed ranges are identical, except for the inversion. Most of the physical magnitudes with which we deal are in the range from our zero to the speed of light, but there are some quantities that extend beyond the natural zero levels. This introduces some modifying factors into the physical relations, as the natural zero levels are limiting magnitudes of the kind discussed in Chapter 17. That is, points at which an inversion of most physical properties take place. For example, a property such as thermal radiation that increases with the temperature up to the unit temperature level, the natural zero, does not continue to increase as the temperature rises still farther. Instead, as we will see in Volume 3, it undergoes a decrease symmetrical with the increase that takes place between zero and unit temperature. A somewhat similar reversal occurs in the case of these properties that extend into the region inside unit space, the time region, as we have called it, because all changes in this region take place in time, while the associated space remains constant at the unit level. Ferromagnetism is a phenomenon of the time region, and its natural 0 point, the Curie temperature, is therefore a boundary between two dissimilar regions rather than a center of symmetry like the speed of light, the natural zero of speed. Instead of following the kind of a linear relation that is characteristic of the properties of the regions outside unit space, the relation of ferromagnetism to temperature has a more complex form due to the substitution of the spatial equivalent of time for actual space in this region, where no change in actual space takes place. No detailed studies in this area have yet been undertaken, but it seems evident that in the more regular elements, the magnetism is subject to the quantity 1 minus x squared to the 1/2 relation that applies to other time region properties examined earlier, and to a square root factor which may also be interregional. It can therefore be expressed as m equals k times the quantity 1 minus t squared, the quantity to the 1/4 power. If the magnetization is dated as a fraction, is stated as a fraction of the initial magnetization, and the temperature is similarly stated as a fraction of the Curie temperature. The constant K is eliminated, and the values derived from the equation apply to all substances that follow the regular pattern. Within the limits of accuracy of the experimental data, the reduced magnetizations thus calculated are in agreement with the empirical values as reported by D.H. Martin. Because the internal magnetic charge is applied against the basic rotational motion of the atom, its force is symmetrically distributed in the same manner as the gravitational force. But as we have seen, ferromagnetism is a motion of an individual, specifically located component of the atom. The directional distribution of the ferromagnetic force in the reference system is therefore determined by the atomic orientation. If each atom acted independently, the orientation of the atoms of an aggregate would be random. But in fact, each magnetically charged atom exerts a force on its magnetic neighbors, tending to line up these neighboring atoms with its own magnetic directions. This orienting effect encounters mechanical resistance and is ordinarily limited in scope. For this reason, and because the relation of each magnetic aggregate to its magnetic environmental changes from time to time. Let's try that sentence again. For this reason, and because the relation of each magnetic aggregate to its magnetic environment changes from time to time, the magnetic orientation of an aggregate is not usually uniform. Instead, the aggregate is subdivided magnetically into a number of sections, generally called domains. Ordinarily, the domains are randomly oriented, and the effective magnetic force is reduced by the distribution over the different directions. Application of an external field forces a reorientation of the atoms to conform with the directions of the field, the extent of which depends on the strength of the field. This reorientation concentrates the magnetic effect in the direction of the field and results in an increase in the effective magnetic force, reaching a maximum, the saturation level, when the reorientation is complete. Okay, that's the end of Chapter 22 on magnetic materials. Chapter 23 starts up, and that is called Charges in Motion. And we will get into that tomorrow. Today, I guess we'll call it short here by 10 minutes or so. And start up here with Chapter 23 tomorrow. Thanks for tuning in today, and have a great day.